So good evening, everybody. Welcome to the idea talk for tonight. We've got Austin Egri. Egri, I'm so sorry. It's going to talk to us about this cool project that's been going on since last summer, right?
Last spring.
Last spring?
Yeah.
In the spring. Motion capture for the RPI hockey team. And he'll go into a lot of detail. Just a couple of the usual logistics. We are streaming live. This is being recorded as we stream. It'll be available later, assuming that it goes really well. And we've got a couple of his team members as well as the mentor here tonight, so it's really excellent. So feel free to ask questions.
Yep.
All right. Thank you very much, Austin.
Thank you. All right, so hockey player identification and tracking. Brief overview, some of the background and motivation for the project, then the identification of players and the network used to do that, then tracking and how we stitch the players together from frame to frame in a video, some issues and simplifications that we went over, or that we identified during the course of the project, and finally some future work. So currently, what does data look like in hockey? This is from the NHL, which typically has better metrics than most leagues because they have more money. They basically have, they track events, so goals, shots, hits, turnovers, some examples, the location of the events, timestamps, and it's all hand annotated, so there are tons of errors. On the left, is the shot map from one of my favorite hockey teams, Buffalo Sabres, and this is the shot map from one of our best players, Jack Eichel. So you can see a lot of every dot is a shot, and where the big shapes and symbols denote goals. So and the colors and symbols are different based on the type of shot. So now if we can take a look at two players, Jack Eichel and Jeff Skinner, both on the Sabres, and they play on the same line together. Eichel is a much better shooter and carries the puck a lot more, whereas Skinner is a much more opportunistic player, like burying pucks in and around the goal, and you can see that from their goal map, or their shot map and goal map. Eichel's shooting from all over the offensive zone, and Skinner has a lot of goals in and around the goal, the crease. So now I have a brief video, and so that's a bit of a overview of how what data and stats look like currently in the NHL. So keep in mind what our goal is. How can we include that?
How well do those methods tend to do? Like, can you often predict who will win a game, or is it very noisy?
Typically, the best predictions I've seen have been just around 60% accuracy, which isn't great, but better than guessing.
But I don't think you're looking to predict. You're still on track, right?
So
what shots happen, right?
So hold on. I'll get there. All right. So here we have a clip of the Buffalo Sabres. So we'll just watch this real quick. So we have Eichel coming in on the right. There's the puck. There's a shot, and Skinner buries the goal.
Yeah, we can actually. Yeah.
You have to move your
There we go.
Okay. How do I?
It's working.
I don't see that.
What's that?
It was coming up. There we go. That's working right now.
All right. I can't see that on my screen, so I apologize. All right, so here's the play. I thought I would have it preloaded and it would work really well. I guess not. So anyways, what we're gonna see is an event where Eichel and Skinner are coming down the ice. Eichel and the Sabres take a shot, and they're vastly outnumbered, but that doesn't matter. So we see the shot coming right now, and there are 4 defensive players in the zone, but none of that. But they aren't really like covering anyone. So if I told you that there are 4 defensive players and like 2 offensive players that are really involved in the play, that would sound like something good for the defense. But the puck bounces right out to Skinner in the front of the goal, and the defensive players aren't in the way of the shot. They aren't defending anything. They're kind of just there. So what we want to take away from this is how can player locations on the ice at the times of these events impact, or how can we use that to read what is, to dissect and understand what is going on in a play. Mm-hmm. In this particular example, the goalie was out of position, the defense was out of position, and it was a really easy goal from this shot. Had the defense and goaltender been in position and prior to this, then it'd be much more difficult. So, yeah. And to replay it one more time. Yeah. So the goalie was on his, or the right side with respect to the camera of shot, and could not get back in time to stop the play. So let me go back to the slides here. Okay. All right. So that's a brief example. Eichel is, and all right. So now this gets us to our objective for the project, where we want to get player locations to better understand the game of hockey and combine these with the events that are already known. So especially with regards to goals, assists, plays like that, we have the shot maps, but how can we further understand the game? I can tell that Eichel is a player that carries the puck a lot more and shoots from the outside from the shot map, and that Skinner typically varies rebounds, but we don't have an analytical way of measuring that. We can see Eichel shoots from further out, and that's kind of where that stops. So we would like to obtain the player locations and their movement throughout a play to better understand what can happen next, and is that the optimal way of playing? So to answer your question, Andres, ideally we'll be able to take a set of locations where the puck is and any events that just occurred, and be able to predict what the next event, or the probabilities of the next event, and ideally optimize what the players should be doing. Like from a coach's perspective, if the coach sees a player always have 2 options, and the player just defaults to the lower percentage chance of scoring, then you want to coach them to take the higher percentage route. So prediction is definitely something that we would like to, or that prediction is definitely a motivation behind the project.
It's interesting. If that theoretical framework was to be put in place, then you could presumably simulate the perfect game.
Exactly. and it's like, yeah, so given the data, of course.
Well, there's lots of implications. I mean, you could use it, so you could predict games, okay? You could create synthetic games. You could use it for coaching to try to shift things in, but you could also use it for player assessment, right?
Exactly.
Yeah.
And you can evaluate your players based on like, okay, I should I should play player A over player B because player B takes the puck to a low percentage area most of the time, rather than a high percentage area. But he obviously isn't doing this on purpose, or he doesn't know that, okay, I'm hurting our team's chances of scoring. He's still trying to play the best he can. So by having more information, the goal is to optimize that.
The goal is to get goals.
Yeah, give up fewer goals.
Yeah.
So as a more technical objective, we'd like to identify and then track players from the single broadcast camera feed. Most hockey games have a single broadcast camera feed, so it's easiest to work at all levels of play and at all hockey games. And from this, we'd like to obtain, and from that we can get player image coordinates. And once we have those player image coordinates, we'd like to transform those coordinates onto an XY grid of a hockey rink. If we look at much like the example before, where you have all the XY grids, that's not the same as the player's coordinates from the image ring, like we saw in the video. So we would like to use, to identify the players in the frame, in an individual image, I'm taking advantage of a pre-trained network called Mask RCNN. This is a region-based proposal network. So it starts off with a convolutional neural net that breaks down the image into for like a computer understanding level, and then proposes three things: the bounding box on various objects. It proposes a class for the object within the bounding box, and a segmentation for the mask. And we can see in the frame all the way on the right, you have the bounding box around a person and the segmented body shadow of the kids playing soccer. So this network was originally trained to do this for 80 different classifications, and they found that this approach, where you're actually identifying the segmentation of the object, performs better than simply identifying the bounding box, even though it's a harder problem. And to train it, they took into account the loss from classing, from the class prediction, the bounding box accuracy, and the mask, which is your segmentation. So now for tracking, we need to stick to using Mask RCNN, we identify people in every frame from a video, and after that but we don't know which person corresponds from frame to frame. So
is the entire network that you use already pre-trained, or do you have to like train like a final layer at the end or something to adapt to your specific image format?
So I forgot to mention this. Thank you, Alex. One of the classes that this network was pre-trained on was people. So, and I found that it works very well identifying people from hockey images as well. Further training is something that I plan on looking into. But it has not been a top priority because identifying people has worked fairly well. But yes, so like as part of the future work, we'd like to separate referees from players on the bench, maybe. So to track, so now we have the segmented images of each person. But you don't know where the person goes from frame to frame, but we can take advantage of the fact that video frames are sequential, and there's only so much movement that occurs in sequential frames and in sequential video. So I have a player voting formula that is dependent on the detected bounding box of the player in the past frame and a proposal player in the current frame. So we take the intersection of the bounding boxes and divide it by the union of the bounding boxes to get an IOU score. And then we compare the image similarity, and then we compare that to the image similarity, and we use that IOU score and the image similarity to determine which players should be paired together. The image similarity comes from feeding the images into Inception, and we can take the transfer layer of Inception as a vector that describes the image, and that's how. And we can take either the cosine similarity or the L2 norm of those vectors to compare how similar images are. And the similarity score with the lowest value is matched together. So now I have a brief demo of the identified players and their stitched together locations. And the fact that we can get all the colors of each person the same is showing that the players were stitched together correctly. So one of the couple of the major issues with this is person occlusion. So when one skates in front of or behind another, it's very difficult to identify them. If you only see one person in the image, how do you handle that? And also, like I was saying earlier, this network was trained to identify people in images, not specifically hockey players. So when it first runs, you detect all sorts of people, the referee, people on the bench, people in the stands, none of which affect the play, which is what we are trying to evaluate. So we simplified. So to simplify that, we have a human initialization step to select which people identified by the network are the specific hockey players that we care about. And we've decided to focus on rush plays to minimize the possible occlusions, where a rush play is much like we saw in the video. There's an offensive team coming down on defensive end with typically a decent amount of spacing between the players, and this will and rushes in hockey are a high scoring chance play, because typically the offensive team has more players than the defensive team and has a good shot at scoring. So for our future work, we're still working on how to automatically transform the image from the image view to a top-down view of the rink. So we are working on a data set to learn specific rink coordinates from the image, and from that if we can identify those automatically, then we can just perform that transformation as we analyze the video. And we can go directly to XY coordinates and we don't have the mid step of player coordinates within the image. And we would also like to start performing predictions on on plays and build a data set of plays in hockey, specifically on the rush. We'd like to include more cameras within the rink to follow the play throughout the entire, so rather than having a single camera follow the players on the ice, we can just watch the entire rink and the players all move throughout that. And hopefully identify specific players rather than players per team. And finally, we'd like to train the network to recognize specific hockey players and to eliminate the human initialization step. And if we can start a sports analytics program.
I thought you had some images of the XY of projection.
Overhead.
Yeah.
Yeah.
Can you bring up some of those? Those are, I mean, there's a lot of artifacts that I've seen that you guys have done that's very cool that you haven't shown.
Well, the big issue with the transformed overhead is it's completely manual.
Yeah, correct.
You have to manually label 4 known locations on the ice, like a face-off circle or where one of the lines meets the boards or something like that. And then go to the rink overhead image and label the same 4 places. And then that allows you to calculate a transformation matrix. So that human intervention is painfully slow.
How often do you have to do that?
But it's very cool.
Well, we were doing every 10th frame, and that seemed to be enough, but there's 60 frames a second. So even 10 seconds of video is quite a lot of work.
So it's not tracking, it's not like an initialization thing like with
Well,
players.
the initialization that Austin was just referring to is for what he just showed you is you got to, in the very first frame, you got to select which player is which. And then from then on, the stitching pretty much takes place automatically.
It's deterministic, right? It's not a learning process, right? It's like given the current player in the current frame and the next frame, you run the intersection thing you were talking about for the boxes, and then you get a
the only AI is the selection of all of the people-like objects in the frame, and it's totally in isolation. The next frame, it'll select all the people again, but it doesn't know from one frame to the next who's who.
But you do train the network in the beginning to identify the hockey players, or do you
So
just
that's another thing which would be cool to see.
The network as it exists
Is before
now
you
will
got
find
the
balloons and doggies and
the video
appliances and people
of
and all sorts
before
of
you got tracking
We're just using it to
working.
find people. And
You know, when it's
hockey players
switching
fit that
from frame to
category
frame
well
to-
enough so that it
I do
finds
have
them
an
without any problem.
example
So
of
it's not
that, yeah.
That's very cool.
Okay, I can pull that up.
I mean, it helps show
It's
what
not
the,
assuming-
but I would like to see the example of the projection
The
just to
AI?
kind of show,
No, it's just
because there's some interesting things about that.
find all the people,
Right, okay,
a completely new
so this
run.
is kind of the.
Here's the next
overhead.
frame,
Okay.
find all the people, and then the
So-
stitching that he was talking about. Here's some of the.
Oh, no, that's it. So this is just like an example of the overhead coordinates from a rush.
Mhm.
These were hand annotated because to get the overhead transformation. But the goal of this is to do it automatically, so we don't have to.
So that's what we're trying to do is to automatically select the landmarks from the video camera frame.
So how are you guys going about creating your data set for that? Are you just manually annotating?
Well,
Are you guys,
the input right now is just RPI hockey video frames,
I was,
unannotated. We have to do everything else.
right, I'm saying one way to get annotated data would, I mean, you just take a camera and then somehow be able to, well, basically just make your own film, but in that film, you have it deterministically be able to determine what's what, like, I don't know, put like a green dot above everything that you want, and then like later edit that
Well,
out.
that's effectively what Austin's done here. It's found.
Can you bring
all
up
the
that,
people, and then what the
The-
human
the
interference
changing
starts
color
with
one?
yeah,
I'm looking for it.
okay.
telling the algorithm that is now going to stitch from frame to frame, telling it which one of those people you want to consider.
Right, I was,
To what extent has this been done in hockey and also in other sports? Already?
And NBA has got something that they're doing like this. NHL was apparently trying to do this, and they gave up, and I think, and they're just using RFID tags. So they've tagged all the players and the puck, and that works fine.
That's
If you can do that.
Is that what NASCAR does?
I don't know what NASCAR does.
Oh, yeah, show that one.
Does the NBA have a solution to the player occlusion problem?
So, this is like.
Yeah, it's called
just
refs.
Running
Spread out, guys.
an algorithm on all sorts of people and wide.
So this would be really.
This is just the AI result.
Yeah, you should have shown this earlier to kind of give the appreciation of the problem. I mean, well, this is really interesting because it's showing, it's showing how poorly attended RPI hockey games are. My God.
That was from one of my club games.
Oh.
Okay.
I mean, this looks like a Dartmouth game.
But yeah, so like you have lots of people identified, and
So, and then you applied both the selection of who you wanted to track
yeah,
and
stitching.
the stitching to get that previous one.
So wouldn't actually using basically persistence of motion across frames and modeling that, wouldn't that help you maintain?
So one of the biggest problems with this is the rotating camera. So
Right, but so if we, I'm saying is, so actually, I don't know how much the model you're using corresponds to actual, the current theories of human vision. But, we don't look at single pictures. We look at basically continuous spread. And the kind of what we see is what we see at one moment is conditioned by what we've seen, previously.
exactly.
And so we have a lot of circuitry that basically makes huge assumptions about object coherence and persistence.
Right. And so some of the so some of the state of the art kind of deep learning like tracking systems, I guess, with the moving with an independently moving camera there's a lot of work to be done.
If you go out on the web and look for an outfit called Face++, you will see, you can see little videos of how they've tracked people in a crowd, but it's all from fixed camera position.
Right, and I'm not saying that
So, but what we're trying
Do you
to
have,
do here is another level above that because the camera's
An image of that flattened, of the flattened rink
But what
photo?
I'm saying is that if there's a
Just
biological inspiration.
No, but I mean the actual photo of that. There's one of the flattened rink where you see the shadows of the players.
The overview is your eventual goal, right? And so like once you have the overview, once you have the overview with the colors, even if the colors are different, it's fairly easy. Now you have like a stable view, right? Once you have the overview, and then you can match across frames. So it seems like once you tackle the overview problem, this becomes a non-problem, or at least much less of a problem.
for the occlusion?
For between frames tracking the player.
I don't know.
well, it's pretty reliable now, and
Oh, I think, so what you're,
we've already talked about this.
yeah, well, I think,
We
yeah.
haven't convinced ourselves that it's going to help, but we're going to try.
So I think what Charlie's saying is if you can map to the top-down XY, we ought to be able to, you're essentially saying
well, then you
where.
have the same problem as other people have with the fixed camera.
Yes.
But and I think at least in a relatively easy way to do that is you can create your own massive data set easily because you have a hockey rink that you can film at, and while you're filming, if you can somehow locate the key points that you want to be able to translate on, and you locate that, so while you're filming, you have some way to also track where those are, then you don't have to manually annotate it, and then you just created a training set.
And that's why we want to use the overhead cameras. So you have fixed position, fixed field of view overhead cameras. So you have a complete view of the whole ice all the time.
Right, but what I'm saying is even from this,
I'm talking about motion capture, like.
Yeah. I mean, that's.
Yeah. Now, what you're talking about is what we're really working towards right now as an intermediate goal. We have the camera view, and you can find the players and then stitch them together from frame to frame, and then you can turn that whole video into an overhead view.
Are you saying you have to do that manually now?
Well, it's the turning into the overhead view that is manual, and that's the thing we're working on to automate. As soon as we can automate it, then we can use a combination possibly of the overhead view and the camera view to fix busts in the stitching, or to just do it completely at that level.
I was just trying to give a suggestion of how you could make a training set for the automation. Because right now you have to manually annotate the points, but if you have a big data set of here's a picture and these are possible points, then that's good. And I'm saying that you might be able to create that by making your own film and having the points on your film be just like annotated. Like I said, you put like a green dot on everything. That way when you're filming, you see that green dot. But then later,
it's really tough to do this in real time because of the computation behind this.
Do which real time?
Well, as soon as you get an AI in there, at least the AI that we're using right now.
So you're
also, does it have to be real time?
So you're talking about like
we would like
putting something on the physical rink, correct?
I'm just for making a training set. Yeah, you put something on the physical rink, then you take video of everything, and then you edit out the physical things that you put there.
Right.
Now you have a huge video where you have the annotations, and you also have original footage that doesn't have those annotations on it. And
so you're talking about building an AI to determine what the transformation should be to overhead.
Sure. Yeah. Yeah.
And we've thought about that and we've considered it. But right now the route that we're taking is non-AI, simply because we already know that applying the transform once you've got it is very, very fast. It can work in real time. So if we can find 60 frames a second.
Okay.
So if we can come up with an equally rapid way of determining the inputs to calculating that transform matrix, and we already know that if we do the transformation matrix every 10 to 15 frames, it's just fine. So we don't have to do it every frame. Okay. And right now the approach is we're just trying to find straight lines on the ice. You know, the blue lines, the red lines, the goal lines, the base of the boards, top of the boards, anything that's a straight line, because those are obvious landmarks on the ice, and we just need 4 points someplace in those obvious landmarks, and that gives us what we need to calculate the transform matrix.
Well, are you trying to solve the hockey problem? Or are you trying to solve a more general object persistence problem?
Yes and no. Right now we're working on hockey because it's easy video.
Right, but
it's pretty much a white background.
So
don't you
small
worry?
countable number of objects to track.
Well, yeah, but you're kind of leaking your abstractions around though by doing by basically making a bunch of assumptions about what you can do to transform to overhead. So if you're
we're not assuming anything in the transform to overhead.
Do you have like a sketch of your tool chain?
Relies on
like a
labeling 4 known locations on the ice.
Like your workflow kind of a thing.
No.
You're assuming that there's 4 known locations that you can map to.
Well, you could.
Well, we already know there's plenty of known locations on the ice.
But you could talk about it.
So that kind of answers my question, even if you don't realize it. You're looking for hockey.
We're solving the hockey problem first, yeah.
Well, the hockey problem is the unique thing. They don't have to solve it for football. Well, actually, they could solve it on the low end. What I was hoping Austin could spend a few minutes talking about is kind of tools. You've mentioned some things, but I was going to ask you, talk about how you're using the idea cluster. Are you using the GPU machine, or are you but just generally talk about kind of your tool chain.
Yeah, so a lot of the development is in Python. I am taking advantage of pre-trained networks to recognize and understand images, specifically masked CNN and Inception. Not having to train those saves a lot of time and energy. And yeah, so like we're just examining video, object recognition, object tracking. Yeah, let's get like kind of a background of sports.
So you're doing a lot on the cluster, but you're doing it like on node 3. You're not using a GPU machine, or are you also using a GPU machine?
I use node 2 with the GPUs to analyze lots of images at once.
Okay.
The masked CNN starts with a lot of so it's like pre-computes the image masks for every image, and then we stitch those masks together and throw out the ones that are of people that you don't care about.
What's been your experience with the GPUs and running this code on?
A lot faster.
What's been other people's experience while you're running your stuff?
Have you run into
Hopefully not using it.
Have you run into any problems?
Yeah, there is an issue where it appears to. Oh well, cut the stream. Yeah, where running the network on more than 31 frames appears to crash something. I'm not sure why.
That's interesting.
Yeah.
Have you talked to David about it?
And then start over again.
No, I think I did, and he seemed to think it was a network thing, but it wasn't like anything different that I did. A network meaning the algorithm.
Oh, I see. Not the network.
But yeah, that kind of got put on hold.
Well, in terms of the CNN stuff, that kind of stuff, is that from like the Google code, or what is that from?
The masked CNN or Inception?
Yeah. Well, just
masked CNN is an algorithm originally developed at Facebook Research. I'm not using their specific implementation of it because the installation is really difficult, and I asked David about it, and it's kind of like, and I found something else that works, so I just moved towards using that. It was an open source implementation, and Inception is a Google network trained to identify objects in images, or to classify images as specific objects. So it, and that's why the transfer layer works as a vector image comprehension, because from there it's a simple regression to the image classes.
all right. Any more questions for Austin?
I'm just curious about the biological underpinnings of the Inception model.
Of Inception?
Yeah, like how much is it, I mean, do they bias it towards just the
Cats. It does a really good job in cats.
You know, how close does it match what we do as humans?
Oh, I'm sorry, I can't answer that. Classified?
Well,
No, not how well,
No.
but how, like the structure of the deep network.
Yeah.
I mean, the fact that we use deep neural nets is because our brains are deep neural nets, they're not flat.
Yeah.
Like,
Well, I mean,
so,
the answer to your question is we don't know how our brains work, so,
but we do. We've gotten a pretty good sense of that in terms of.
well, you may know where in the brain it happens.
well, there's some.
We know this, I mean, what we know about how the brain works is like saying, yeah, he's using node 3. Okay, I don't think we know it any better than that biologically, do we?
We know a bit better than that. We know kind of how
If
things
you're
are
talking
set.
about visual perception, then yeah, we have a very good idea of what input gets to our brains.
Yeah.
Besides that, like consciousness. But
No,
that's not what you're
I'm just
about.
talking about, so you don't have to think about the fact that I'm me and that I'm still here instead of jumping over there. And that's a unconscious process that
But
we're
these
taking advantage of.
networks,
Can you-
state-of-the-art networks now?
Can you go full on that?
Nothing
Oh,
that
yeah.
is tied with actual biological research is state-of-the-art currently.
Just full on the inception slide.
Neural networks, deep learning stuff is completely separate from
Well,
psychology.
I mean,
biology.
how many neurons,
I
how
think
many
you're-
nodes are in this AI? 200?
Nodes,
Yeah.
way more.
I also don't think that, I
Well,
mean, I think it's
is
just
it
like-
anything close to the number of neurons in the visual cortex?
Well,
But that has no basis, like you can't
Does
just
it?
compare the numbers there.
right,
Well,
because I mean, a
Right,
fly,
I mean, and I haven't even asked you how
There
many
is.
connections are with
but a
each.
fly does object persistence.
I'm sorry?
A fly does object
Sure,
persistence.
sure.
And it has probably closer to how many
Right,
neurons
but-
you have.
I mean, the other thing though is that a lot of the advances in deep learning nowadays are just if you have a network that works, can you train a smaller network to scale it back that just replicates the original network with a certain percentage accuracy? And we can do that. So knowing the number of networks, or knowing the number of nodes in this network is relatively meaningless because we already know that.
Right, and I'm not asking about you guys were asking about the number of nodes, I wasn't asking.
Well, I'm just
about
using
nodes.
that as a measure of complexity because
Right.
I don't know any other way to measure it right now.
But I don't think that's a good measure
Yeah,
because
I don't.
Well, if somebody can come up with a better one, I'm all ears.
But so my point is more that there's in the past 20 years, we've gotten a much better sense of the modularity of visual systems in the brain, and there's a certain modularity built into this model. And I'm just curious how much of it follows. Did it end up being similar in any ways? Is it doing edge detection in the same way? And does it because if it's doing some of those things, or if we could train one to do that, we could build on what we know about object persistence in the human brain, or even in the fly brain.
It sounds to me like what you're asking about is the neural net itself. Are you trying to dissect it and say, well, we know that, when we look at something, our brain interprets the shape and the color and different things like that, and sort of breaks this all down into pieces, parts, and then assembles it back into some coherent thing that we can identify and follow as it moves. Now, where is that happening in the neural net? Because obviously the classification process has to break down the image into certain components. But I don't think you can go into the neural net itself and say, this is where it finds, the edge of the face or the ear or something like that. I don't think you can do that.
Someone built this model experimentally to this task. It wasn't just trained from nothing. I mean, you could look at it, it's modular.
128 layers.
What?
Said this is the only thing we're gonna do. Yeah.
Yeah, exactly. They're not gonna, they went through a process of figuring out how this is going to work.
But I can't believe that it was a process of cause and effect, or it was, here's the training data, and I'm sure a lot of it was just empirical. What works better than something else. I don't think that you can train in that fashion.
I don't think he's asking if this network is inspired by biology. I think he's
Well, it
saying
clearly isn't.
right now that we have this network, how well does it correspond with what we
Right,
do?
that's what he's asking, and I think that I think what you have is, it is it's an analog, it's experimentally derived, it's been heavily influenced by current performance characteristics. It's probably different now than
It's
it was
completely
when
influenced by the training set.
well, but what I'm saying is,
I mean,
that the architecture of these networks it's
How much is topology influenced by
Yeah,
it?
the architecture isn't training
Yeah.
independent.
Yeah, the weights are, sure.
But what I'm saying is, this stuff is also, you cannot consider this modulo the performance. Okay, they're spinning the dials based on the training sets they're throwing it, but they're also spinning the dials based on what kind of performance they have, the CPU performance that they have available, and that's going to change.
But I don't think that's the questions that's being asked.
No,
here, though.
but what I'm saying though is yeah, hasn't been able to figure that out. And also, so, and I finally, this question, and then we have to stop the broadcast, is how is this going to contribute to another 33-3 season? Is it going to?
It will have no effect this season.
Tom as an alum, John as an alum, we're sorely disappointed. Although he never saw 33. Actually, I never saw it either. It happened right after I graduated. So
I'd like to
it is sad, and I did get to see Adam Oates play.
I got to see us beat Ken Dryden twice in the season.